Welcome to the Explainer. Today, we're talking about forces. You know, those invisible pushes and pulls that are responsible for pretty much everything, from how you're sitting in your chair to how the entire solar system holds together.
So let's start with a big question. What is it that's keeping your feet firmly planted on the ground right now, but at the same time is also keeping the moon locked in orbit way up in the sky? Well, believe it or not, the answer is the exact same thing: forces.
So here's our game plan for this explainer. We're going to start with the absolute basics. Then we'll dive into the spooky forces that you can't actually see. We'll get into gravity's big pull, clear up the whole weight versus mass confusion, and finally, look at how all these forces work together to change motion. Let's do it.
All right, first up, let's talk basics. We use the word force all the time in everyday life. But what does it really mean when physicists talk about it?
At its core, it is super simple. A force is just a push or a pull. That's it. And its job is to make something change. It can change an object's shape, make it speed up, slow it down, or change the direction it's going.
And this is a perfect way to visualize it. Imagine a tennis racket striking a ball. That's a huge sudden force that completely alters the ball's speed and direction. The arrow there shows us exactly what the force is doing. It points in the direction of the push, and the longer the arrow, the more powerful the force.
Now, most forces we bump into every day are what we call contact forces. They literally have to touch something to work. We're talking about stuff like friction, which slows things down, or air resistance, that feeling of the wind pushing against you when you run. Even the ground pushing up on your feet right now, that's a contact force.
So how do we measure the size of these pushes and pulls? We use a special unit called the Newton, written as a capital N. And yeah, it's named after the one and only Sir Isaac Newton, who basically wrote the rulebook on all this.
Okay, but what about forces that don't need to touch anything? This is where things start to get really weird and interesting. We're talking about action at a distance.
Yep, it's true. These non-contact forces can push or pull on an object across totally empty space. It kind of seems like magic, but it's just really cool physics.
You've definitely seen this in action. Ever run a comb through your hair and then used it to pick up little bits of paper? That's static electricity, a non-contact force. Same goes for magnets. They can attract things like iron filings from a distance, creating these amazing turns without ever touching them.
Okay, so static and magnets are pretty cool, but there is one non-contact force that is way more important. It rules over everything we do every single second of our lives. Any guesses what it is?
Of course, it's gravity. It is the universe's main attraction, the ultimate long-distance force that literally holds galaxies together. So let's take a closer look at this big pull.
Now, this is kind of a mind-blowing idea. Gravitational force is the attraction between any two objects that have mass. The more mass something has, the stronger its gravitational pull. That means you, right now, are pulling on the Earth just as it's pulling on you. And this diagram shows it perfectly. It's a two-way street. The Earth pulls down on you, but you are also pulling up on the Earth with the exact same amount of force. So why doesn't the Earth come flying up to meet you? Well, simply put, the Earth is just so incredibly massive that your tiny pull has basically no effect on it.
Okay, this brings us to something that trips a lot of people up, and it's a really important distinction to make. Let's talk about the difference between weight and mass, because they are absolutely not the same thing.
So here's the deal. Your mass is just the amount of stuff you're made of, all your atoms and molecules. It's measured in kilograms, and it is the same no matter where you go in the universe. Your weight, on the other hand, is the force of gravity pulling on all that stuff. And since it's a force, it's measured in newtons, and it can totally change depending on where you are.
And this example just nails it. Look at this astronaut. Their mass is always 72 kilograms. That's true on Earth, on the Moon, on Jupiter. It's constant. But check out their weight. On Earth, it's 720 newtons. On the Moon, with its weak gravity, it's only 180. And on massive Jupiter, it would be a crushing 957 newtons. Same person, totally different weights.
And speaking of the Moon, let's just bust a common myth right now. There is absolutely gravity on the Moon. It's just a lot weaker than Earth's, about 1/6 as strong. If there were no gravity, those Apollo astronauts would have just floated off into space. That bouncing around they did, that's what weaker gravity looks like.
Okay, so let's put this all together. We know what forces are. Now let's see how they actually create action and change the way things move in the real world.
A skydiver's journey is a fantastic way to see this. First, they jump.
The force of their weight pulling them down is way bigger than air resistance pushing up, so they accelerate. They get faster and faster. But as their speed increases, so does the air resistance. Eventually, the upward push of the air perfectly balances the downward pull of their weight. At this point, the forces are balanced, and they fall at a constant speed, which we call terminal velocity. Finally, they open the parachute. This makes the air resistance force massive, much bigger than their weight, and they slow way down for a safe landing. It's a perfect dance of competing forces.
So, we've talked about speeding up and slowing down in a straight line. But what about turning? Well, objects naturally want to keep going straight. So, to make something move in a circle, you need a continuous force pulling it towards the center of that circle. We call that inward pulling force a centripetal force.
And here is the big zoom out, the cosmic connection. That exact same idea is what keeps satellites and even the moon orbiting the Earth. The satellite is moving sideways at an incredible speed, so it wants to just fly off in a straight line. But Earth's gravity is always there, constantly pulling it inwards, acting as the centripetal force that keeps it trapped in that circular path.
So this leaves us with one final fascinating question to think about. If Earth's gravity is constantly pulling satellites towards it, why on Earth don't they just fall down and crash? Well, the kind of mind-bending answer is they are falling all the time. But they're also moving sideways so incredibly fast that as they fall, they constantly miss the Earth. They are literally falling around the planet forever. Pretty cool, right? Thanks for joining me on The Explainer.